Yes, in the previous class, we have discussed that the important feature of the Zener diode is in its reverse bias condition. Okay, right? And so that is the reason, okay, we have seen this circuit where the Zener diode is connected in its reverse bias condition. And we have also seen the characteristics of the Zener diode. Okay, right? Next, let us see the detailed mechanism of the breakdown in Zener diode. Okay, the breakdown in Zener diode is known as Zener breakdown, right? Of course, in an ordinary PN junction diode also breakdown takes place. That breakdown is known as avalanche breakdown. Okay, so first we will discuss about the avalanche breakdown, right? So this also I have told you in the previous class what happens in avalanche breakdown. Okay, right? When we increase the reverse voltage, the charge carriers will travel with high velocity. Okay, more the velocity, more is the kinetic energy, right? Now, these electrons which are traveling with high kinetic energy, or these charge carriers which are traveling at high velocity, what they will do is they will collide with the atoms, okay, and they will release more number of charge carriers. Now again, these new charge carriers will further travel with high velocity, and they will, okay, further collide with few more atoms, okay, and they will release few more charge carriers. Okay, so this is called as carrier multiplication, right? That will result in large current. Okay, that is the avalanche breakdown. So let us see the points one by one in detail. Okay, so breakdown due to avalanche effect. Remember, this is for ordinary PN junction diode. Okay, right. If reverse voltage is increased at a particular value, the velocity of minority carriers increase. More the reverse voltage, more the velocity of the charge carriers. Then, you know, kinetic energy is half mv square. Okay, velocity is more, means kinetic energy is also more, right? So, reverse voltage increases, velocity increases, which means kinetic energy of the charge carriers increases. Okay, right? But under reverse bias condition, what are the charge carriers which are flowing? The minority charge carriers. Okay, that is the reason. Due to the kinetic energy associated with the minority carriers, more minority carriers, okay, are generated when there is collision of minority carriers with the atoms. So what happens? Under reverse bias condition, you have the minority charge carriers flowing. Okay, so when we gradually increase this reverse voltage, the minority charge carriers will start traveling at high velocity. They will collide with atoms. Okay, right? And when they collide with atoms, so this is like, say, take a stone, hit mango tree. What happens? You are throwing one stone. When the stone hits the mangoes, okay, the stone also comes out, the mango also comes out, right? Okay, similar effect. An electron goes and hits an atom. Of course, the electron comes out of the atom, it knocks out few more electrons from the atom. Okay, right? And these new atoms will further collide because the voltage is still there. Okay, they will further collide with the neighboring atoms, and they keep on releasing charge carriers. Okay, so this is called as carrier multiplication. Okay, right. So what happens? The electrons, okay, the minority carriers get accelerated due to high reverse voltage, collide with atoms to generate what? Okay, more minority carriers. It is like one stone going and hitting mango, right? Stone is out of the tree, mango is out of the tree. Now suppose this mango and stone, they go and hit another mangoes. Okay, more number of mangoes are released. In this example, I spoke about stone, mango. Okay. Here we have the charge carriers, the minority charge carriers. Okay. So what is happening? More number of charge carriers are generated, right? This is called as carrier multiplication. Then finally, large number of minority carriers move across the junction, breaking the PN junction. Okay, right? Gradually increase the reverse voltage. What happens when we gradually increase the reverse voltage? The charge carriers are traveling with high velocity. They collide with atoms, knocks out more number of charge carriers. Okay, of course, minority charge carriers. These charge carriers will further collide with atoms. As a result, large number of charge carriers are generated, right? Current is due to the flow of charge. So more the charge carriers, more is the current, right? So this large number of minority carriers gives rise to very high reverse current. Okay, this effect is avalanche effect. Okay, and the mechanism of destroying or the breakdown of the junction is called as reverse breakdown. Okay, or also known as avalanche breakdown. Okay, of a PN junction. Remember, this is primarily for a PN junction. Next, the voltage at which breakdown occurs is known as the reverse breakdown voltage, or also known as the avalanche breakdown voltage. Okay, right? Anyway, so this is about the avalanche breakdown. Okay, right? Next, we will see is Zener breakdown. Now, remember, avalanche breakdown, it is in general for a PN junction. Okay, whereas Zener breakdown is particularly for Zener diode, right? So, what happens in Zener breakdown? This also we have seen in the earlier class. That is, when the doping is high, the width of the depletion region is thin. Okay, so the breakdown will happen at low voltage, right? So, how the breakdown takes place? Because the width of the depletion region is thin, okay, for the reverse voltage, the electric field intensity generated is high. Okay, right? You know very well, a stick which is very thin, you can break it easily. Okay, right? So what happens? You are putting less effort, but you are able to destroy the bonds that are present in the stick, and you are able to break the stick. Same logic. Okay, what happens? Because the width of the depletion region is thin, right? A small voltage can break the depletion region. Fine. So what happens? See, stick is thin. Small effort is sufficient to break, right? You are only putting small effort, okay, but at the molecular or atomic level, that is becoming high to break the stick because the stick is thin. Same thing with electric field intensity. Okay, right? The electric field intensity now becomes very high, although the voltage is less. Okay, because the depletion region is thin, the electric field intensity is high. Okay, so what that high electric field intensity will do is it will pull out the charge carriers from the bonds. Okay, or rupture of covalent bond takes place. Okay, and that leads to breakdown, right? Okay, so that is the Zener breakdown. Now, let us, this is the outline which I have given. Now let us see point by point. Okay, you know, Zener diode is heavily doped PN junction diode. Okay, Zener diode is also PN junction diode, but it is a heavily doped PN junction diode. When doping is more, we have discussed this several times, the width of the depletion region is thin, okay, or narrow. Next, Electric field intensity is voltage divided by distance. Okay. If distance is more, electric field intensity is less. When the distance is less, electric field intensity is high. The formula for electric field intensity is voltage divided by distance. This also we have seen when we discussed the transition capacitance, CT, first unit, when we discussed CT, derivation of CT, transition capacitance. There I've told you electric field intensity is inversely proportional to distance. The formula for electric field intensity is voltage divided by the distance between the two plates of a parallel plate capacitor. Okay. For diode, it is voltage divided by distance. That distance is the width of the depletion region. Okay. So what happens? High, okay, electric field intensity is generated because the width of the depletion region is thin. Okay. High electric field intensity, what it will do? It will pull out the electrons from the valence band. It will simply break the bonds, pull out the charge carriers. More the charge carriers, more will be the current. Okay, right? So let us see this. This also in the previous class we have seen. Let us see this point by point. So when a PN junction is heavily doped, depletion region is narrow. Okay. Electric field in next point. Electric field is voltage divided by distance. Okay. So E is voltage, the applied reverse voltage divided by the width of the depletion region. Okay. So E is V by D. D is small, so E is high. Okay. E is inversely proportional to distance. Width of the depletion region is thin, so electric field intensity is high. Such an intense electric field is enough to pull the electrons out of the valence bonds of the stable atoms. This high electric field intensity will pull out the electrons from the atoms. Okay, right? So what is happening? You are pulling out the electric field is pulling out the electrons from the atoms. So large number of charge carriers are generated. Large number of charge carriers are generated means the current is high. Okay, that is the Zener breakdown, right? Next, such a creation of free electrons is called Zener effect. Okay, this is Zener effect. Okay. Yeah, one of you please confirm if you are able to hear me. My voice is clear. And whether you are able to see my screen also.
Yes, sir.
Okay, right. Fine. So what happens in, okay. Right. So what happens in the Zener diode? The high electric field intensity will pull out the electrons from the valence bands. Valence band is the outermost, okay, outermost electron shell. I hope you know energy band diagram. Okay. Valence band is simply the atom, the outermost set of electrons. Okay. That is the outer, or you can say it as the outermost energy level, right? Okay. So that is the valence band, right? Then such a creation of free electrons is called Zener effect. Okay. So what happens? What is Zener effect? When you gradually increase the reverse voltage, at one point the electric field intensity becomes sufficiently high, and that high electric field intensity will pull out the atoms from the valence band. Okay, we will pull out the electrons of the atom. Okay, that high electric field intensity will pull out the electrons from the atom, right? And because of that, large number of charge carriers are generated. Large number of charge carriers means large current. This effect is known as Zener effect. Okay. different from avalanche. See, avalanche, what happens? The charge carriers, the minority charge carriers are traveling high velocity, they bombard with atoms. Okay, it is like stone hitting the mango tree. Electric field intensity is different. Okay, this particular Zener effect based on the electric field intensity is different compared to the avalanche breakdown. Okay, clear? Fine. So the minority carriers constitute large current, right? Mechanism is known as Zener breakdown. Okay. So we have seen avalanche breakdown, Zener breakdown. Okay. Next, coming to Zener breakdown, obviously, okay, we will consider this in the special diodes, okay, Zener diode, right? And always the Zener diode, we are operating in its reverse breakdown condition, okay, right? Because forward it is similar to ordinary PN junction diode, no special role there. So we are using it in the reverse bias condition. Okay, next, let us see the comparison between Zener and avalanche breakdown. Okay, Zener breakdown due to electric field intensity, whereas avalanche breakdown is due to the collision of accelerated means traveling with high velocity. Okay, charge carriers with adjacent atoms, and that leads to carrier multiplication. Okay, right. Next thing is any breakdown less than 6 volt is known as due to Zener effect, right? Occurs for Zeners with Zener voltage less than 6 volt. Avalanche breakdown if it is greater than 6 volt. Okay. For example, say you have Zener diode. Breakdown voltage is 6.2 volt. Then you say that the breakdown is due to avalanche mechanism. Okay, the breakdown is due to avalanche mechanism, right? Okay. Next, temperature coefficient is negative. What do you mean by negative temperature coefficient? Means if temperature increases, the breakdown voltage decreases. Okay, let me show you the characteristics and explain. So Zener diode has negative temperature coefficient, means see the breakdown is, for example, now room temperature breakdown is happening here. Okay, right? So if temperature is increased, the breakdown will happen at lower voltage. Okay, the breakdown will occur at lower voltage. Okay, that is the meaning of negative temperature coefficient. The same point is given next. The breakdown voltage decreases as temperature increases. Okay, as you increase the temperature, the breakdown occurs at lower voltage, right? For example, the breakdown of the Zener diode is 5.1 volt at room temperature. Gradually increase the temperature, it might break down at 5 volts. Okay, right? Whereas avalanche breakdown has positive temperature coefficient, means if temperature increases, the breakdown voltage increases. Clear? Opposite. Next, the IV characteristics is very sharp in breakdown region for Zener diode. Okay, means for Zener diode, okay, this is very sharp. Current rising sharply. Okay, not gradually, right? Current is rising sharply. Whereas in the avalanche, for the case of avalanche breakdown, the current is not rising suddenly, but gradually rising. Okay, the IV characteristics is very sharp in breakdown region for Zener breakdown, whereas for avalanche breakdown, the IV characteristics not that, okay, not as sharp as Zener breakdown. Clear? Next, this also we have seen Zener diode as voltage regulator. Let us see that point by point. Okay, so first of all, why do you need regulator? Okay, the plug point that you get AC. For example, if you want to charge mobile phone, okay, you need DC voltage, right? Not only mobile phone, laptops, there are DC motors, okay, right? There are many, say, logical circuits which work on DC. You have seen DSD lab, right? They are giving 5 volts DC, fine. So there is a lot of requirement to convert AC to DC. In the process of converting AC to DC, first step, this also we discussed earlier, first step you use step down transformer, because the electrons, the electronics, in electronics we are requiring lower voltage, so step down. Next, we are going for rectifier, okay, right? Rectifiers also we have discussed in first unit. Next we go for filter, again we discussed this in first unit, right? After filter, okay, to maintain constant voltage we connect the regulator, and at the output of regulator we can expect pure constant DC, okay, that point is given here, right? Next, okay, just a minute. Yes. Okay, so next we will see, okay, we will see how we can use Zener diode as a voltage regulator. Okay, this one we have outline, we have seen point by point, we will see now. Okay, outline we have already seen in the previous class. Next, Zener diode as a voltage regulator. A shunt voltage regulator using Zener diode is shown in figure 4.1. Okay, this one, right? 4.1. This also we have seen in the previous class. Same circuit, this one, okay. Zener diode is operated in reverse bias. So, okay, the negative terminal or the cathode is towards the positive. To protect the Zener, we are connecting resistor. So, resistor Zener diode, right, to operate it in the reverse bias. Across the Zener diode, we are connecting load. So, only 3 components. Okay, I think there was a disturbance again. Please confirm if my voice is clear and you're able to see my screen. Yes, one of you please confirm.
Yes, sir, we can see.
Right, thanks. Okay, so to operate the Zener diode in the reverse bias condition, a resistor, then okay, we have the Zener diode, right? Zener diode maintains constant voltage across it, fine. Although the current through it changes, it maintains constant voltage across it. So this property we can use in voltage regulator, okay, right? So here, obviously, the circuit that we now have will be simply R Zener diode. In addition to that, a load resistor RL. Okay, so R Zener diode, and in parallel to that Zener diode, we will connect. Okay, in parallel to that Zener diode, we will connect RL. So very simple circuit, right? This will act as voltage regulator. Means this particular circuit, although the input voltage changes, still it will maintain a constant voltage across the load. This we have discussed in the previous class. Let us see point by point. Okay. Zener diode has a characteristic that as long as the current through it is between Iz min and okay, fine. So okay. So let us go ahead with the discussion. This point, the Zener diode has a characteristic that as long as, okay, as long as the current through it is in between Iz min and Iz max, the voltage across it is constant and equal to Vz. Okay. So what is told here means, if you look at the characteristics, okay, of the Zener diode, when the voltage varies, okay, when you gradually increase the reverse voltage, at one point, although the current changes between Iz min and Iz max, okay, the voltage is constant. This constant voltage is Vz. Okay, that is the point here. Next, as Zener diode is connected in shunt, okay, with the load, the output voltage is equal to the Zener voltage. Zener diode maintains constant voltage across it, right? Okay, Zener diode maintains constant voltage across it. Fine. So the voltage is constant. Whatever you connect there, still the voltage is constant because the terminals are the same. Okay, right? Example I told you. Suppose what do you get in the plug point? 230 volts, right? Although you are connecting fan, TV, fridge, tube light, okay, till it is 230 volts, right? Because there is a constant supply which is coming out of the plug point. Of course, that is AC, right? The same logic is valid for DC. Zener diode maintains a constant voltage across it in the breakdown condition, right? Now, whatever you connect, still the voltage is constant. Means the voltage across this RL is now constant, which is Vz. Okay. So V naught is equals to Vz. We have seen this, right? And applying KCL here, I is equal to Iz plus IL. Okay, right? Then IL, what is the load current? Ohm's law, V naught by RL, right? V naught is equals to Vz. Just now we have seen. So IL is V naught by RL, or you can say Vz by RL, because V naught is equals to Vz. So putting Vz here, okay, putting Vz there, we get, putting, okay, in place of V naught, Vz, IL, you can say it as Vz by RL. Okay, next, this equation we have seen, right? And here there are two cases we will study. First, okay, When input fluctuates, if the output is constant, then only it is a regulator. Okay, right? Next, if you change load, okay, for example, there is a 5-volt battery. Okay, if you connect a DC motor also, the 5 volts should not change. It should not become 4.5. Still it should be 5. Okay, or you remove that, okay, motor, you connect phone, you want to charge your phone, right? Okay, still it should maintain the 5 volts. Okay, then only it is useful, right? Okay, so two cases we will study. First, regulation with varying input voltage means if input changes, the output is constant or not. Okay, we have to consider. Next, if keep input constant, okay, right, or to study the effect of variation in load. Okay, standard process, any subject. Okay, say you want to study the effect of variation of one entity. Okay, then you have to consider the case whether the other entity is constant. Suppose, okay, to study the effect of change in RL, you will consider the case when Vn is constant. If both are changing, you don't know what is happening. You can't figure out what is happening. Okay, right? That is the standard process. So when Vn is changing, whether the output is constant or not, for that you will take RL constant and proceed. Next, when RL is changing, whether the V0 is constant or not, to understand that, we will consider the case when V in is constant. Okay, for changing RL, you will take V in constant and analyze. Okay, then only you can see the effect of the change in RL. Okay, so first case, regulation with varying input voltage. This one we have already discussed, okay, earlier. So I'll give you the outline we have discussed. Now we will see point by point. Okay, load current IL is V0 by RL. Okay, right? This one you can see very easily. Ohm's law, IL is V0 by RL. Okay, right? Next, so because V0 is Vz, you can take it as Vz by RL, right? And here, case 1, when input is changing, I told you we will take RL constant, right? So remember, case 1, RL is constant, Vi is varying, this one. Okay, so RL is constant, Vz is anyway constant, the property of the Zener diode. So IL will remain constant. Okay, the same equation we are writing here, right? So now what happens if Vn increases? We have seen this again in the previous class. If Vn increases, I increases. If I increases, okay, right? If I increases, IL is constant because RL is constant. So Iz